So for our next talk, think about how when programs join a distributed system or when you join a new team, certainty is lost very quickly. And we find that linear thinking is not enough. But then what is? Please welcome to the stage Jessica Kerr, who podcasts on Greater Than Code and Arrested DevOps. Currently, she spends much of her time building syntheses through industrial logic. Welcome, Jessica.
Thank you. I am happy to be here today at Craft because this conference, as best we can, we're coming together to share common questions and ideas from throughout the many fields of software development. I want to talk about another occasion. 75 years ago, March of 1946, in the Beekman Hotel in New York City, another group of people came together to talk about common questions and ideas that they had. They called it the Macy Conferences for Circular Causality and Feedback Mechanisms in the Biological and Social Sciences. It was right after World War II. Now, before World War II, people could pretend that science was apolitical. But in World War II, that was not a thing, because they all saw that if Hitler won the war, science would be sent back by centuries. And then worst case would be if Hitler got the atomic bomb first. So many scientists across the world went to work for the Allies. And Allied science is a big reason that the Allies won World War II. For instance, during the war, Norbert Wiener, he was one of the people at this Macy conference. Norbert Wiener, a mathematician, he worked on surface-to-air missiles. So they're trying to shoot down the planes that are bombing the cities, and it's really hard because a plane is a really little target far away, back with the missiles that they had. But the other thing that they had that helped was radar, very early radar. So after they made a guess about where the plane would be and where the missile would go when they actually shot it, then they could shoot the missile and they could watch the missile and see where it actually went and where the plane actually went. And Norbert Wiener was working on the part where they used these measurements, even in the noisy radar that they had, to feed into how to aim the gun next time. So you've got this loop of you shoot and then you see what happens and then you adjust for the next shot. It's a kind of learning loop. And it reminded Norbert Wiener of the sensory motor loop that we use. So when I want to grab something, I reach out my arm and I don't grab it blindly. That's harder. I'm constantly making adjustments until I can grab my water glass just right. So Norbert Wiener noticed this similarity, and this is what the conference was about. He helped bring together this group of people to the Macy Conferences for Cybernetics. Okay, we shortened the name to the Macy Conferences on Cybernetics after the word that Norbert Wiener coined. And they were looking at communication and control in machines and animals because they saw the similarity. So they brought together a diverse group of people. We've got neurophysiologists, psychologists, ecologists. Then there's mathematicians and physicists and anthropologists and a sociologist. And for this group, a lot of them found a camerata in these conferences. I met first in 1946 and 10 times over the course of 7 or 8 years. Many of these people got back together. And it was formative. They each put out a lot of fascinating work and they did a lot of interesting work together. I want to talk about 2 of the people who are at this conference and contrast them and their philosophies and where they took cybernetics, because both of these philosophies are very crucial to software development today, and we're really good at one of them. That one is John Von Neumann's. So John Von Neumann, most people have heard of. He is the greatest rational mind the world has ever known. I am not exaggerating. So at 26, he's born in Hungary, but by 26, he's a full professor at Princeton. And he worked down the hall from Albert Einstein. But they didn't collaborate very much because Einstein was too slow. Von Neumann was incredibly brilliant, and he did work in a lot of fields. In addition to being incredibly smart, he was a nice guy. Everybody liked him. He threw great parties. For von Neumann, the road to success was a many-laned highway with little traffic, which is good because he was a terrible driver, just terrible driver. There's a quarter at Princeton that they named after him because he crashed there so many times. People were always getting him out of trouble. But in general, he was good at rather a lot of things. This is his known for list from Wikipedia, and it's ridiculous. Of course, we have the modern computer architecture. He was the big proponent of putting data and code in the same memory banks. He worked on information theory. He worked on game theory. Logical automata was one of his favorites, and a zillion other things. And he advanced every field that he touched. Von Neumann, so he was very big on all of this logical stuff, and he advanced all of these fields. During the war, he worked on the Manhattan Project, and he was very important there because he's both working on computers there and on math. And he worked out the math and got the computers, built the computers in order to work out the math, to find the right mechanics for an implosion bomb. And that let us drop an extra bomb on Nagasaki because we didn't have enough refined uranium for another of the simpler bombs like we dropped on Hiroshima. Von Neumann was one of the first people to conceive of the computer as essentially about logic, as a logical machine to implement reasoning, whereas everyone else saw it as an engineering problem, electrical engineering. So in that sense, he was one of the first computer scientists. He was at the Macy conferences on cybernetics, hoping to learn more about brains, because he saw that his work on logical automata and stuff could maybe move in the direction of the human brain, give us a model of the human brain. At the Macy conferences on cybernetics, he met Gregory Bateson. Now, Gregory Bateson is very different. He is an anthropologist and a zoologist and ecologist and psychologist. He worked in a lot of fields too. He had a lot of influence in many different areas. But where von Neumann worked on information theory, Bateson worked on communication. And for instance, like before the war, he was in New Guinea studying the Ayatmal people, this like native tribe. And one of the things that he observed and wrote a book about was phenomena of schismogenesis in the tribe, where people would like get mad at each other and the tribe would start to split. And then there were certain rituals that the tribe would do that would bring them back together. His studies of schismogenesis were put to work during the war when he went to work for the US intelligence agency, spreading propaganda to try to induce schismogenesis in enemy fighters. He was pretty happy to get away from that and get to the Macy conferences. At the Macy conferences, Bateson was looking to find ways of bringing stronger theories and more rigor to the social sciences. But instead of information theory, he cared about communication. And instead of game theory, Bateson studied play. For instance, he went to the zoo and he looked at the monkeys, and he noticed that the monkeys, they sometimes like smack each other and bite each other and wrestle around. And sometimes this is fighting, but other times this is play. And you can't know from any single individual action, any single individual physically delivered message, whether this is play or fighting, what the meaning of it is. That comes in the meta message. So Bateson looked at levels of communication and noticed that there's the content of the message, sure, but there's also what's going on outside of that. So in the monkey's case, there's a meta message of this is play sometimes. I see this in all human communication, of course. It's totally a thing. For instance, in dating, you go on the first date and yeah, you find things to talk about, but really the meta message is always, do you like me? Do I like you? Do you like me? And then later in a relationship, as you're starting to get closer together, then there's a lot of things you talk about, but there's always this subtext of, are we okay? In our teams, take a pull request. And there's a comment typed in there that says, your curly brace is in the wrong place. It belongs on the previous line. Okay, technically accurate statement, but what's the meta message there? Well, there's, if you belonged here, you would know this already. Or there's, I can make you do more work, even though it's so dumb that a freaking computer could be doing it. Or maybe we've been arguing about curly braces over the last couple of days, and I'm just giving you crap. It takes a lot of context to know that something like that is play. But there's always a meta message in every message. And the first thing that hits us about any given message we receive is what it means for the relationship between us. In software, we can look at this. If you zoom in really small and get really specific about a particular communication, particular message going back and maybe forth between a server and a client, then you can speak about this mathematically, how much information is transmitted, which messages are valid. But then when you zoom out a little more, zoom out over time, you notice that, okay, that protocol changes. We upgrade it. We upgrade our ability to send more meaning in the messages. And then you realize that there's a meta message in the version of the protocol used. And then you might choose to make that explicit. A lot of modern APIs do make this explicit, where you always have to say the version of the protocol that you're using. And then once we have that meta message explicit, then we can learn from it. We can learn which clients are still using the old version and how many and how often. And then we can widen the system to include the people that maintain the software, and we can talk to them and say, hey, please upgrade. When we zoom out and we look at the meta message, at these layers of communication, that's one pattern of systems thinking, because the meaning is always at a higher level. In general, the kind of reasoning that von Neumann wants to do, the logical stuff, it always works in the small. We always have to get to that incredible level of precision that we can reason about and know what the computer's going to do in order to write code. And von Neumann worked to expand the range of where we can do this, to expand it to games that have any set of fixed rules with exactly 2 players, and to expand it with logical automata to see how interesting it can get when we're using precise fixed rules. Bateson took a different direction. He always cared about the context, and he always looked a little wider. So Bateson studied things like, he was a pioneer of family therapy, this idea that the relationships matter. An individual's psychology is by no means independent of the people they interact with every day. And this is true in our software too. Relationships matter. So look at this little client here. No, yes, this is the client. And the client really wishes it could just make a function call to get this data, but it has to go over the network. So it's pretending it's doing RPC, and it's like, the networks suck. I'm just going to retry until I get what I want, and then I can return something. But this isn't working very well. If you zoom out and consider the server as part of this system, then you recognize that if the server has some little blip one day, maybe it's garbage collecting, that results in a failure, and then it gets slammed with retries, and then it goes down. Now you have real problems. Widening the system can help us do a better job at coding the client. For instance, now we'll introduce exponential retry, and we'll be like, okay, I'll try again after a second, and then 5 seconds, and then 30 seconds. And that's a big improvement. The server has some chance to recover. Until you widen a little farther and realize that there's all these other clients involved, and they're all sending at exactly 1 second, and exactly 5 seconds, and exactly 30 seconds. And so the server goes down repeatedly. This is called the thundering herd. And now, when we consider this wider system, we realize that it helps to put some random jitter. So we'll retry at approximately 1 second, approximately 5 seconds. And now the server isn't going to be slammed by everything at once. I enjoy that randomness actually makes this better. There's a pattern here of every system is a subsystem. Every system we build, every system we are and personally take part in is a subsystem of a wider system. And we can do our work better when we zoom out and realize that. Now, in this client, when we zoom into the small and we're writing the code, this is math. We totally use math to implement this correctly. But what correct was depended on seeing the wider system. So this happens in functional programming. Our goal is to extend the scope of what we can be precise and reason about as wide as we can, to keep our code data in, data out, so that we can test it, so that it's deterministic, even if it's random with a particular distribution. This helps us get more code correct and also find it easier to think about. But at some point, of course, the reason that we're doing these calculations is to have some side effect on the world. And we need some state from the world. And there's a person. Bateson recognized that the computer is an arc of a larger circuit. This straight line of data going through that functional code is part of a circle somewhere, which always includes a person and an environment and messages going around. Math helps us get us correct. Systems thinking gets us to what correct is. And this gets us back to what is systems thinking. And the Macy conferences, we can go back to the name of the conference before it was shortened to cybernetics. The Macy conferences for circular causality and feedback mechanisms. These are like the core insights that led to cybernetics, which evolved into systems thinking, among other things. So circular causality, for instance, in that thundering herd problem is, well, there was a failure, so we'll retry, which causes more failures. This is circular causality, and it's incredibly common in everything above, like rocks and billiard balls bumping into each other. As soon as biology or people or learning is involved, there's circular causality. Like in a very small sense, if I snap at my teenager for something, probably because I'm having a bad day and they were just in the way, and they snap back at me, and then I yell at them for being disrespectful or something horrible. I would never do that, but other people do. And then they yell at me, and then we just get in this loop, and we don't even know why we're yelling at each other after a while. The interaction is its own system. Circular causality is everywhere. It is normal. It is what makes life interesting, and it's what holds the social world together. In this case, the thundering herd problem, we can notice this, and we can choose to use the meta message of the failure, which is, I'm the surfer and I'm having a hard time. We can use that to choose whether and when to retry. And then we weaken this other half of the loop so that we don't cause more failures. There was circular causality in Norbert Wiener's missiles. Why did you hit the plane? Because we shot it just this way. Why did you shoot it just this way? Well, because some wind and weather and stuff. And also because the last time we shot it this way, it did this. And why did you shoot it that way last time? Well, because some stuff, and the previous time we did, there's a loop in there, and that loop represents learning. In general, in systems thinking, I always want to look for these loops. Some of these loops are reinforcing loops, like when one failure leads to lots of failures. That's a reinforcing loop. Some of these reinforcing loops are great, like network effects. Facebook is more useful the more people use it. And the more useful it is, the more people use it. And then the more useful it is, and the more people use it. And this is that hypergrowth loop that startups love to get. It's a reinforcing loop when we get madder and madder at each other, or when we fall more and more in love. In our code, we see reinforcing loops of, hurry up and get this done, just hurry and get it out there. And so the code winds up messy, and that means the next thing takes longer, which leads to more rush, which leads to more messy code, and then you get the big ball of mud. Normal. Nuclear fission. There's a reinforcing loop for you. The bombs dropped on Hiroshima and Nagasaki depended on molecules of uranium or plutonium splitting apart. And they split apart, they release neutrons, which hit nearby uranium or plutonium, and those fission. And then you get enough of a critical mass that this reinforcing loop is strong enough that boom, you get an explosion. There's other kinds of loops to look for too. For instance, when Bateson noticed the reinforcing loop of schismogenesis, if you're doing it wrong, no, you're doing it wrong, no, you're doing it wrong, no, you need to wear a mask, no, don't tell me to wear a mask. And we get further and further apart. The tribe had rituals that they would do to bring the tribe back together. That forms a balancing loop. So balancing loop is the second kind to look for. Reinforcing loops and balancing loops. Reinforcing loops makes things stronger and bigger. Balancing loops keep things where they are, keeps things not static, but dynamically stable. Balancing loops kind of hold the world together. So control rods in a nuclear reaction represent the balancing loop inside the power plant. We want some fission, but not too much. So we're going to insert the control rods when it gets too strong. Driving a car, whenever I start to go out of my lane and I get grom, and then I go back into my lane, or the car buzzes at me for leaving my lane. This is a balancing loop. This kind of constant little error correction and adjustment. This is normal. In our code, an automated test is a balancing loop. And that we want our code to do one particular thing. When it stops doing that thing, we get notified. Now that balancing loop only works if, as a human, I respond to that red test by changing the code or changing the target. In code review, that's not how we do things here. Balancing loop keeps things the same. In general, with systems, when you're looking for why you're doing something, you need to zoom out at least until you find some sort of information loop. Now that's zooming in and out from the tiny precision that we need in order to code to the bigger and bigger pictures that determine why we're doing this. That's a lot of work. But you need to do it because meaning is at the next level up or higher. Norbert Wiener can get really good at shooting those missiles at that plane, but it's only in the context of a battle and a wider war that he would know which planes to aim at. So writing correct code can be an exercise in logic, but knowing what correct means, that's an exercise in systems thinking. John Von Neumann was incredibly good at this zooming in and out. He could move back and forth between the super deep math of automata theory and the engineering, and then he'd back up and do politics and schmooze with people and get those projects funded. Because his early work on computers wasn't just how to put them together and wasn't just how to use them, how to write software. It was also how to get them built, how to get the money and the people in the place to get them built. And this is as we get from mid-level to senior to influencing in our companies, this is the kind of zooming out we have to do. Now, John Von Neumann, in his work, he really enjoyed aiming for universality. Information theory applies to any message. The meaning is irrelevant. game theory applies to any two-player fixed rule game. But watch out for that. Especially in custom software, it's tempting to write something generic and universally applicable and reusable. But the reason we're writing software, custom software, is so that we can change it. And when you reuse software, you wind up with these loops of these webs of causality of I changed this and that happened and this happened and this happened. Danger. Context matters. Bateson recognized this. Bateson always cared about context, and he looked for patterns of wholeness instead of just universality. Whether it's a microscopic drop of water or the planet wreathed in cloud, systems thinking looks for wholes, it looks wider, and it looks deep at the relationships, not glossing over them to make it generic. So if we care about wholeness, we'll care about, climate change, but at a much smaller scale in our software. We'll care about error messages as user interactions and recognize that we can make them help and guidance messages to bring people back. We'll care about the whole life cycle of data so that we can migrate it and delete it and export it and migrate it to the next system. And we'll recognize that in our work as software developers, we don't get to call it done when we move it to production, because you might think your job is to implement features and take them from ready to done, but that is an arc in a larger circle of operating useful software. And this whole circle, if we look at this whole system, if we can participate in as much of the system as possible, then we can make our software better and better. Because our job is not to implement features, it's to provide ongoing capabilities that the rest of the company and our customers can use. And when we look at it that way, we see this circle, we can make it a spiral as we get it better and better. And continual improvement is our job. So when that library is out of date, we update it. And this is another pattern of systems thinking. There's a bunch of others. Eventually, I'll write these all up at systemsthinking.dev. I'll get there. So keep your eye on that site. Meanwhile, I want to go back 76 years to when the United States dropped 2 bombs on Japan, in Hiroshima and Nagasaki, and 200,000 people died. Not all at once. Half of them died that day, and the other half trickled into hospitals over months with their hair falling out, their skin reddening and vomiting, and the hospitals couldn't help. They just died of radiation poisoning. Science is not apolitical. Scientists built those bombs, and they weren't happy about it. After the war, they formed associations to advocate for disarmament, for let's not do this anymore. All the scientists of the Manhattan Project joined, well, not all of them. Von Neumann, he didn't join. He was like, oh, no, only technical nature. This is because he wanted to continue to participate in government. Because he thought the Soviet Union was definitely the bad guy. He thought, well, game theory, that's math, and that's what's happening in the social realm. He scaled that up to worldwide politics and said, all we can do is build more bombs, and then they'll build more bombs, and then we'll build more bombs. How is this reinforcing loop supposed to help? Von Neumann was a big advocate for more bombs. He was like, you say bomb the Soviets on Sunday, I say why not today? You say bomb them at 5 o'clock, I say why not 1 o'clock? The reason he wanted to build computers, I mean, other than that they were fascinating, a logic machine, was to build a bigger hydrogen bomb. That's what he wanted. And maybe, if that is the greatest rationality the world can ever know, maybe rationality isn't the best. Maybe it's not the only thing we need. Bateson recognized that when we apply the theory of games, we reinforce the rules. We make people think that we're unchangeable, but we're not, because we need to play. And the rules are not constant. It's not the business of science to inherit the earth, but to inherit the moral imagination, because out that, man and beliefs in science will all perish together. John Von Neumann was in love with the aristocracy of the intellect, and he had a highway to success. Bateson did not. He struggled financially, but he recognized that if we win against our environment, we destroy ourselves. Every system is a subsystem. We do not exist independently. Bateson saw the world as one mind, one big learning. His daughter Nora coined the term symathecy, learning system made of learning parts. He saw that communication was more important than information, and play brings us novelty in ways that games don't. And as software developers, we have a laboratory of systems. We are constantly working in systems that are subsystems of subsystems, and we can change them, and we can make them observable. We can participate in that complete loop of providing capabilities and becoming better. We can learn. And my hope is that as software developers, we will learn to be better at systems. And when we recognize that our work is never apolitical, we can apply that learning that we take from working in systems, that our actions have consequences that we can't see, but we can try and we can notice and we can learn. If we can apply that in our wider world, then maybe we can help bring our culture together, and maybe we can leave a better world for our children and grandchildren 75 years from now. Thank you.
Thank you. It is rare that we get such an inspiring and emotional talk at the tech conference. Thank you very much for doing this.
Thank you.
Let's see if we can get both of us up on the screen. We don't yet have any questions just yet, but I'm sure that they will start rolling in pretty soon. Until that's happening, I need to call out quickly that, not fitting the theme at all, that the sponsor gift raffle is going to happen right after this talk and Q&A finishes up. So like 3 minutes to 6 p.m. Central European time, head over to the main stage for that. But for now, just pop your questions into the Q&A part of Hopin, like Renee did, asking, do you have any starting points for a developer except Jerry Weinberg?
Except for Weinberg. Donella Meadows is the other one. She approaches this from a climate perspective in her primer for systems thinking. It's a good place to start. Personally, my current favorite is Heinz von Forster's Understanding Systems, but that's not in print. And last I looked, it was like $100 on Amazon for this tiny book. When we are trying to relate systems thinking specifically to modern development at systemsthinking.dev. This is a project of Kent Beck and me, and we're also running workshops. We have a workshop coming up in a couple weeks through Skills Matter, so that's available. Yeah, there's a lot of different sources of systems thinking. I find all of them useful. Indeed, the person mentioned Jerry Weinberg, and he wrote specifically about systems thinking in software management. So that's very relevant, a little dated, but also Weinberg is like a hilarious author. His Secrets of Consulting is one of my favorite books.
Yeah, thank you. We also have Matthias asking, what do you tell people that you want to create a montage line on software from design to development to QA to prod, and every step is done by different persons? That's not breaking the loop.
Yeah, so there is a circle here, right? We don't just implement features to have code and files. We wrote that code for people to use. And so there's always a circle that eventually involves people other than us using it. But the more of that circle we can be involved in as a single team that talks to each other, then the more we can learn. Because when you divide that up, you've just got everybody has their little arc in the circle, and they're focused on that arc, and they'll optimize that arc, which doesn't help the wider system. My advice when you're in a place like that, that's organized like that, and you don't get to choose that organization, is to get to know people on all those other teams. Find out who is looking at the analytics of who uses your software. I mean, ideally, as developers, you can sneak in log statements because you have control, or, I mean, honeycomb events would be better, but you can sneak in information into production that tells you whether people are using it. And that's really important feedback, because, there was a good quote from Cuttlefish yesterday. It's fun to get obsessed by the craft of software when we can't tell whether our work is having an impact, but we can do both. So right, you can sneak in your own loop of what was deployed and what it's doing if you have access to production logs, for instance. But in general, get to know the people in your company and those other teams. And it's actually hard. It can be totally hard to track down who these people are, who is looking at the statistics of how this website or whatever is doing and deciding what to do next. And if you can meet them as humans, which was a lot easier when you could meet them in the office, but that's okay. You can ask them for coffee over Zoom, or you can ping them on Slack or whatever. And if you can get to know those people, then you personally will start to get a perspective of that wider circle and can have more influence over the organization as a whole. And it'll be great for your career, and it'll also be like really satisfying.
Yeah, that sounds awesome. While we wait for any other questions from our audience, I guess a logical follow-up to this is just in general, like if I'm like, okay, so I listened to your talk, but I'm just, I don't want to say a cog in the machine, but like I'm just a mid-level developer at your run-of-the-mill web dev company. Like I'm probably not gonna change the world, but like how do I take this and how do I start applying this in my day-to-day?
Well, so there's always relationships. Systems thinking doesn't just apply to code. It's fun to apply to code because we have so much control over the code compared to like our family. But when something confuses you in real life, when you're like, what is my child's problem? Zoom out, look at from their perspective, see some of the different influences. And especially if you can find some sort of reinforcing loop, you can make a change. Because if there's a reinforcing loop, for instance, of, okay, in my own life, I'm tired, so I don't exercise, so I'm more tired. When I can recognize that, then I can choose to intervene. And I can run that loop the other way. And I can say, I'm tired, therefore I will exercise. It's not what I feel like doing, but true self-care is rarely what you feel like doing. It's what's actually going to help you that you know based on prior evidence. So then I can choose to exercise and then become less tired. And then I can choose, and then it becomes easier to choose to exercise. So this kind of thing really applies everywhere in life. It just takes some conscious sitting back and reflecting. And sometimes it's really annoying because you're like, dang it, I know I should exercise.
Yeah, I'm pretty sure many of us can relate to that nowadays. All right, thank you for that as well.
Thank you. Thank you for running this conference. Thank you for contributing.
Oh, this is the effort of a lot of people. I'm just sitting here just saying words that have been pretty much written from me. So thank you for coming and contributing your wisdom and time. We did prepare a little special gift we can maybe put up on the screen to show it to you. There we go. That's
it's so cute.
So we work on getting that to you in the real physical world somehow, hopefully. But yeah, for now, thank you very much for your time. It was amazing. Bye.